chair, reduction and resilience engineering. Today we have our visitors with us, Dr. Rita Exposito from University of Delft in the Netherlands. Dr. Exposito is a professor, assistant professor of mechanics of masonry structures at the Civil Engineering and Geoscience Department of the Technical University of Delft since 2018. She gained her PhD in fractures of concrete in 2016 from TU Delft, and before that she had an MSc in structural engineering from Parma University. In the period between 2016 and 2018 and more afterwards, she has worked very extensively on the assessing the damage of masonry structures that have been damaged by induced seismicity in the low-lying lands in Netherlands. Based on this experience, she has then developed quite extensively both computational work and experimental work on damage of masonry structures, both at the micro scale level and at the macro scale level. And this is what she's going to talk about today. So without further ado, dear Rita, please, it's up to you. Yes.
Thank you very much for the introduction, Lina, and let's just check if that is. Just put it in presentation. Okay. Which screen is showing? Okay. So we hope you are seeing all the presentation in full slide. If not, please maybe send a message. So thank you very much for this introduction and for being here today. So as said, today I want to talk about some work that I'm currently doing to try to develop an integrated assessment strategy. But first, what do I mean with having an integrated assessment strategy? So we all know that to assess if a structure is safe or not, we need to take some steps about analyzing the structures and also having some information from inspection. So usually we, of course, go to the structure and we try to identify how the structural component is. We try to see if there is some damage, and we also maybe try to knock on the material to try to identify if what are the properties, and based on that we can do some very simple calculation to give a first insight if is everything okay? Oh, doesn't work. Sorry, just a moment.
Yeah, now they can see them.
Okay. So, yeah, okay. So what I was saying is, when we want to assess structure, we can do some quick calculation. But more and more, we are trying to have a better understanding and better prediction of our structural response. So we are using advanced calculation method where we can rely on the fact that we are able to predict how the masonry cracks, so how the building, even if cracked, can withstand still some load. The problem with these advanced computational methods is that if you want to fit this model, you actually need to take quite some samples from your building and even put them, test them up they break. And this is of course not always possible. So what I want to do and what I would like to try to have is that we can still integrate sophisticated models with testing that are destructive or manual destructive to be able to always have this integration between analysis method and inspection such that we know actually which material our building is made of. I don't have to tell you why this is relevant because of course many of our unenforced masonry buildings are all over the world. They comprise just from housing to heritage building to buildings and infrastructure. So this is very relevant to try to keep our urban asset in good condition. But what are the challenges to actually achieve this? So first of all, how can we characterize the model input with economical and minor invasive in situ tests? This is one question. So to try to fit current model. On the other side, can we and how can we create an accurate and efficient model that can be able to predict the response of the masonry structures, but with very limited input parameter? Of course, these two questions will arise also a third question, that is how the structure processing masonry are and what are actually the independent parameters that govern that. But for today, in my talk, I will only address the first two aspects, starting from the first question on the characterization of the masonry. So we all know that the fact that the masonry can withstand, masonry structure can still withstand load even if crack is all due to the fact that the materiality is non-linearity, that with large softening even after the first crack is started. And we know that the important response in tension, compression, and shear are the ones relevant for to address when we characterize the material. So just a small reminder here, when we characterize this nonlinear behavior, we need to actually have both elastic property, strength property, and toughness property. And the latest one are the important one when we want to try to understand what is the residual capacity of a damaged structure. When we think about how to address this property, of course, we can perform destructive lab tests from the single component to the test at interface or to the test of masonry wallets. But these are often not possible when we go on site because they will require to destroy, for example, an entire wall in a building, which is far from possible. And of course, there have been some developments for non and minor destructive tests to be used on site, starting from the philosophy of knocking on the brick with a rebound hammer or ultrasonic test, or doing something more a bit more complex to try to obtain the property of the interface between brick and mortar, or even this flat jack type of test. But if we compare the lab test and the in situ test for our existing structure in these four aspects mentioned here, we can see that the more we want to know, the more we have to destroy the masonry object. So we have to be invasive in terms of testing and in terms of sampling. And this is quite not possible when we are taking when we are considering existing buildings. So in this sense, non-destructive tests are the one we may go through because they are also nice to be repeated many times. But if we have also another aspect that is about the technical challenges that we can have when we provide an in situ, when we use, for example, manual in situ test as the one here, that is the shelf test, we can see that, this still require higher technical skill. Just to give you an example, the flat jet test and the shelf tests are very popular in Europe and US, but not so much. They were not so much popular in the Netherlands. And we also tried to use this type of test to evaluate shear property in masonry buildings, in housing buildings. Well, we tried in our lab, but the question was, okay, if we had a wall that was only double width, and we had to cut a slot to enter this flat jack, then actually this was very difficult already to find the eccentric saw to make this cut, because there was only one in the Amsterdam to be rented. So if this is an example to say how, when a technique is not there, well, it's not so easy to and fast to implement it. So we were trying to find new ways to try to have a bit of all these positive aspects in way to characterize the masonry. And that is where we came up with the core testing. So core testing is very well known in civil engineering because it is done for other material like asphalt, like concrete and rocks. And if you can take a core, so any constructor can take a core, you can easily pack it and bring it to the lab, so there is less chance to damage. And then you can use a standard test rig to be testing and maybe try to do tests such that you can also obtain the toughness property of the material. And the good thing is that if you have a core of 100 or 150 millimeter, that is much less invasive than if you need to take wallets. So you can also repeat the test many more times. So what we did at QDALT, and this I have to say is mostly the work of my former PhD students, Samira Yafari. We had a great opportunity within the context, as Nina said, of building subject to induced seismicity. We had a great opportunity to extract both cores and standard wallets test from existing buildings, but also replicated typical Dutch masonry in the lab and do the same test. So we had this comparison for a large variety of masonry types. And then we tried to do two types of tests. The first one was on compression. So the difference when taking core from masonry or other material is that, for example, if you take it from a concrete, then you simply put it vertically and you press it on the flat face, and then you can get compressive property. But with masonry, you have to keep the same direction in which you extracted. So you also have to cap the core and try to apply some load such to reproduce the respondent under compression. Some of them have been done in the past, and there is even a recommendation from a railway union in which they suggest to use steel couplers to try to apply the load. But later research has shown that high strength mortar capping is more appropriate. So we use that further in our research. The other thing was that up to that time we started, mostly elastic and strength property were the focus of this type of test. So there was not much on trying to also deduce post-peak toughness property from that. And the new things that we were able to do is to do many tests also for field extracted sample with comparison to wallets and triplets. So for compression tests, we use two types of core diameter, one of 100 millimeter and one of 150 millimeter. So if you have a rounding bond in a single width masonry, this will give you the T-shape and H-shape core that you can see here. And when we compare globally the response of the core with the wallets, we kind of find quite similar behavior. The main difference was that in the core, once the vertical crack were formed, then that tend to get larger instead of creating many vertical cracks, like in wallets. And another aspect that we noticed was that at a certain moment, we mainly had cracking only in the part below the capping, getting to spalling of the part that was not kept. And because we noticed that, we decided that to calculate the normal stress for the test, we would have considered the area of the cap instead of the cross-sectional area of the core. Using this, we try to find correlation in terms of strength and Young's modulus from the core testing and the wallets testing for this different type of masonry and for these different type of core sizes. What we found was that was a quite good correlation, almost one-to-one correlation in terms of strength and Young's modulus. And we actually didn't notice much of a difference between the two sides of cores. When instead we try to go to correlate, let's say, post-peak response parameter like the strain at peak and the compressive fracture energy, here we noticed that the correlation was less good, and we could find a difference instead for the two type of cores. Especially for the fracture energy, we can see that the cores dissipated much less energy than the wallets. And this we kind of try to explain by the fact that we have this lower number of in-plane vertical cracks in the core with respect to the wallets. Of course, once you take core, it would be also nice to see if you can identify shear property with core testing. Early research was trying to do that with I-shaped core. So if you have only one bed joint, and of course, if you incline the joint and the different angles, you can find a different stress state from shear and compression. So in this way, this would be comparable to a triple test where we have lateral pre-compression and we shear off the central break. At the beginning, for the core testing, we were simply controlling the vertical load, the vertical displacement of the jet. But later in the attempt to try to also understand if we could get the post-peak response in shear, we controlled the sliding along the bed joint. Yeah, just to understand what is the difference between these two type of tests. The main difference is that in the core testing, we don't have this constant lateral pre-compression, but the normal stress component will vary together with the shear one. So when evaluated the Coulomb friction criteria, we will take the pair of the shear stress and normal stress at the peak. In terms of failure mechanism, both for the triplet and the core, we found that the most of the time we had this type of shear sliding failure along the joint, sometimes also involving the partial cracking of the top brick in the core. And just in few cases, we have this tensile failure, like complete splitting failure of the core, or some tensile failure in the brick while doing the triplet test, especially for field extracted sample. So to try to make a comparison, and especially in view of trying to characterize the response of the interface, we only consider the sliding shear sliding failure mechanisms. When we try to then estimate the property in terms of cohesion and friction angle and try to correlate with the one of the triplets, we kind of found again a good correlation for cohesion and a slightly correlated relation for the friction angle. In the attempt to also estimate the fracture energy or the energy dissipated in this failure mechanism, we had to make some assumption exactly because the two tests are not the same in terms of boundary condition. So at first, we considered for the triplet that only the area between the curve, between let's say the peak and the residual shear stress would contribute to what is called the multi-fracture energy. To actually take off the contribution of an energy dissipated due to friction in this in the core test as well, we subtracted the curve related to the friction coefficient times the pre-compression at each sliding And we calculate in this way the energy dissipated in the core testing. When we try to look to the relation between the pre-compression, the normal stress, and this energy dissipated, we can find that in triplets, we have this kind of linear relation that when the pre-compression increases, you somehow you need more energy. While in the core, the trend was quite constant. And so in this sense, we have still the question, we did not get answered, is this energy dissipated in mode 2 a real parameter to be considered in our model? So there is something more that we are not able to yet understand. So this would be another question, as I said, about the fracture process that still needs to be answered. But the good things about this core testing method was still that in the lab, we are still able to try to get some positive response. Correlating that with the one in triplet test or other type of shear test still is something that we need to continue with. But of course, the core testing is only one method for characterizing masonry, and there may be other ways to try to give engineer answers on which material property they have to consider in calculation. This was one of the aspects that we actually treated in a larger project for assessing the material property, the building to induce seismicity in the Netherlands. And in this project, I want just to mention that we also created a database of mechanical properties for the most typical masonry type in Dutch buildings. We also derived curve for statistical distribution of inter-building variability based on the field extracted sample, and try to define correlation between mechanical properties. Of course, this was a huge effort and almost 6-year work with different partners. And if you want to know more, you can visit the website on structural response to earthquakes from TRIPLET. But what I want to also say is that not always we can do this for every region or every program that we have. So then the other question which I want to make, can we create a model that can work with any very limited number of input parameters, maybe the one we can derive with non-invasive testing? Well, if we think about that, we need to couple the fact that we are testing at the level of the brick and the mortar to a full structural analysis. So to do that is what I try to develop, and I call a user-friendly multi-scale model. To be user-friendly because at the end should be able to perform structural analysis. So possibly it can be implemented in FEM or any other software that is used in engineering practice. But it should still be able to upscale from the level of the brick and mortar to the full scale. So we have to kind of use an homogenization scheme that anyhow it's easy and can provide a fast upscaling, and then can also enter in the structural analysis. And the characteristic should be that all of this should work with a method that is based on limited input parameters that are accessible in the sense that they can be tested on site. And of course, at some moment, we need to say how the masonry will damage, and we need to say what is the criteria and how this propagates. So we need to have a sound description of physical physics behind this, about interaction between cohesive and friction mechanism. But for now, we try to work on how can we create this easy and fast upscaling technique that can work only with limited input parameter. Well, we try to do that by using micropore mechanics theory. So micropore mechanics theory is based on two pillars. One pillar is the use of analytical mean field homogenization technique. This technique is basically based on the HLB solution. HLB found out that if you have an elliptical inclusion in a body, then the stress state inside that is uniform. And with this knowledge, you can actually derive the stiffness tensor of your composite material with elliptical inclusion in an analytical way. But still, we need to describe damage. So coupling this with linear elastic fracture mechanics, Professor Dormio and Ullman Kondo developed the micropore mechanics theory. So the idea was that if one of the inclusion in your system is a penny-shaped crack, you can associate to this crack, you can say that the crack will grow by changing the radius of your penny shape, just based on the microscopic fracture energy derived in terms of linear elastic fracture mechanics. So this theory is quite used for determining the strength of isotropic materials, especially rock and concrete. Here below you can find two examples. On the left is for a rock, where they use different random oriented cracks, and on the right is actually to describe the hydration process in concrete and derive, based on the water cement ratio, the strength property of the concrete. This technique, however, because it's based on linear elastic fracture mechanics, consider only the cohesive mechanism and not yet friction. So the first step to try to develop that was to first consider the homogenization of the masonry, so using the Minfield homogenization technique to go from the level of brick and mortar to determine the stiffness tensor of the masonry. And this work was done together with researchers Baozu, and we recently published this year in a journal paper. So in this stage, I do not consider crack, and we try to verify that this technique would work for typical bond pattern. We took 3 of them: stack bond, running bond, and Flemish bond. And we also try to verify that it can work for different ratio between elastic modulus of brick and mortar. And we compare different type of Minfield homogenization schemes. But of course, the question is with masonry, is this, you have to assume that the mortar is the inclusion into the brick, or is the brick that is the inclusion into the mortar? And also the characteristic of this technique is that you cannot use very complex shapes for the faces. So you have to use elliptical, cylindrical inclusion, or penny-shaped, or spherical inclusion. So this is a very simplified, let's say, representation of the microstructures, let's say, or internal structure of the material. But when we were trying to play with this, we actually found out that one of the two assumptions will not lead to satisfactory results. So we developed a new homogenization scheme where we use the IDD method together with Nernst interpolation. But basically, it works that you first consider the matrix as an inclusion, the mortar as an inclusion, and the brick as a matrix, and then calculate for the opposite case, and then you interpolate the solution. And here you can see for 2 types of bond that our method is the red line is quite close to the finite element simulation. So what you notice here, what you see here is that on the x-axis, you have the difference ratio between elastic modulus of brick and mortar. And this is in a very large range, also to consider possible damage. But a ratio around 10 would be something that, normal to say for elastic property of intact masonry. And on the y-axis, you have again the vertical elastic modulus of the masonry, and with respect to the one of the brick. But of course, we don't want to have only one elastic constant. We want to have to be able to also reproduce the orthotropic behavior of masonry. And here you can see the comparison for all the 6 elastic constants, where our model is in the black dots, and the continuous line are finite element simulation. And this worked very well for stack bond and also for a running bond. We also tried the Flemish bond, and this has a satisfactory result in most of the cases, but not so well for the transversal elastic modulus, so the elastic modulus in the thickness, for very large ratio of elastic modulus of brick and mortar. But okay, then how do we couple this with cracking? So let's use the principle of linear fracture mechanics, and let's assume that we have cracks in our system. So we did that by using the first two-step homogenization. So first we used the previous method to homogenize brick and mortar. Then on top of this, we took a second step where we homogenized the cracks into the solid matrix. We assume that there are only three family of cracks that are penny shaped and that they are orthogonal between them. This is quite reasonable considering that in masonry cracks will be more or less aligned with the direction of the joint. So with respect to other material like rock and concrete, where maybe a random distribution of crack would be more appropriate, in masonry this is quite nice, and the fact that you have only few crack family makes the things of course much simpler. And then we did simple verification tests. So we at first tried to simulate if the direct tensile test. Here there is a comparison with the test from Van der Plein. And we were able to get the post-peak softening response. And the good thing was also that when we tried to do that, we can see that the only crack family that propagate is the one that is actually in the plane of the bed joint. If we simulate the behavior in compression, again, we found typical stress strain curve. Here we also see that the first crack family that start to propagate are vertical cracks into the plane, these right cracks, and then right after, then start to also occur into the thickness, which is also what usually we see in masonry. The other thing, and the good thing of this model, is that we basically can reproduce the complete softening in tension and compression, and the difference between the relative difference between the energy dissipated and also the strength in tension and compression, by only calibrating the first elastic range in tension. So what we need is the elastic property of the masonry and the tensile strength. We also try to predict the shear behavior, but of course the model failed because there is not yet the contribution due to friction implemented in the crack flow criteria. So this is where we will continue on. But if we want to reflect on the fact if this model can be working towards an integrated assessment, we can try to look to the input that the model can have. So we need to know something about the bond pattern and the volume fraction of each constituent, so the brick and the joint, and how are they oriented. We need to know elastic property of the brick and the mortar, and we need to know tensile property or bond property of brick mortar interface. And we expect that we also need to know some cohesion and friction angle property for the masonry to try to calibrate the property associated to the friction. So in turn, this will be either providing direct input to the model or indirect calibration of some parameter. But the good thing is that the bond pattern and the volume fraction we can obtain with some visual spectrum. We simply see the masonry there. This is a great advantage with respect to other models, other materials to which micropore mechanics has been applied, because you don't need to go to the microscope. The elastic property of the constituents we can try to obtain with some non-destructive test if other minor destructive test cannot be applied. We can do a bond range test to try to obtain bond property also on site and use the core testing method or the short test method to try to obtain some shear property. So in turn, we can have a model that has all the input parameter that can be determined on site with a reasonable non-invasive or minor invasive technique. So this is where we are working towards to try to develop this integrated way to have analysis method that can interface with material characterization tests. And on one side, we are trying to use a core testing method to be able to provide complete nonlinear behavior of the masonry with the limited invasiveness. And on the other side, we are trying to develop a user-friendly multi-scale model that can work with just a limited input parameter. Of course, there is much yet to be done before reaching there. Just list a few points. I think one challenge that we still have, for example, for the core testing is to try to get better insight on this toughness property. And one challenge that we have, especially now in the Netherlands with problems on key wall and bridges, is that all these structures are very thick, up to from 60 centimeter to even 1 meter thick, and they are all made of interlaced bricks, so in multi-weedy masonry. So can we use the core testing method to try to characterize this type of masonry? Of course, I still think we need to learn more on how the collision and friction mechanism work, and also try to input this in models. And of course, if we want to upscale the technique to I just presented to have really structural analysis, we need to consider the regularization method. But yeah, still, I think on formulation and try to understand how the fracture works, that we still have something to do. So I leave you with this, and if you have any question, I would be happy to answer. Thank you.
Thank you very much, Rita. We might take some questions from the audience. Maybe Asana, you want to monitor that?
Yes, we have.
Question?
No, there are no questions.
So just ask.
Yeah. If you have any questions, please feel free to unmute yourself and ask.
Madam, can I?
Hello.
Hello?
Introduce yourself.
Hi.
Good evening.
Not so well, but maybe you can try.
Introduce yourself, please, and shout.
I think you may have to speak up a little bit, and then we can hear you, but very, very faint. Say, yeah.
Hello?
Hi, Bala. Is that Bala Subramanian?
Yes, I'm calling. I'm from India.
Yes.
Very nice, refreshing lecture. I have some queries, especially with respect to this shear bond strength measurement. Can you go back to the slide in shear bond strength, madam?
We are very sorry. It's very difficult to understand. Maybe if you type it will be.
Shear bond strength.
Could you please type your question in the chat, because it's not very clear.
Your microphone.
Thank you. Yeah.
Okay, in the meantime, I'll ask you different questions. I don't know if everybody can hear me. So you have done quite extensive testing.
Yeah.
And I just wonder how that testing campaign correlates with previous approaches that you know that there are in literature
For modeling,
for the testing, the experimental testing. So you have used
we have used basically all the standard tests from the EN 1052, whatever.
Okay.
And and we have done, we have done all of them in displacement control to try to get post-peak behavior. And we have done, again, also the orthogonal behavior in compression, the shear, the out-of-plane bending in the two direction. We also have done some non-standard in-plane bending tests to try to get some property also in that direction.
and how does because clearly this you will have to have done it with fresh mortar, not with the original.
Yeah,
but how does that correlate with your core test?
The correlation for the core test was both from field extracted sample and for replicated sample. We didn't make a distinction there. So, and also we took some data from literature and previous tests that have been done on replicated masonry. So depending on the property that you analyze for strength, the compressive strength and elastic modulus, there was 1-to-1 correlation. And for fracture energy in compression and strain at peak, not so much, because like fracture energy is a factor 2, but the data were more dispersed. But for cohesion and friction, although we had a bit less data, then still the correlation was relatively good, with a factor around 0.9.
Oh, that's very good.
Yeah,
Thank you.
that is.
Thank you. So do we have the
Shear bond strength slide. Triple test. Yeah. Anything out here?
Yeah, madam.
Yeah.
Can you go back
there.
to a few more slides back? Yeah, the yeah. Here, the third diagram in the bottom row, that is a shear test on triplets. Madam, here the pre-compression is applied through reaction-based mechanism, and the shear force is applied at the middle brick, right?
Yes.
Okay, madam. When we are applying the
Is applied to the entire plate with jack. Yeah.
Yeah. When we are applying the shear force on the middle brick, the specimen, all the three bricks at the bed joint try to dilate due to Poisson effect, right?
Yeah, also, yes, yeah, of course.
So it will increase the level of pre-compression, right?
Yeah, but we have a spring that try to control that, and we are also trying to have it in the range. We are usually in the deviation of I think 0.2% of the applied pre-compression that you have, the one that's given in the standard, and we may deviate just slightly a bit when we reach the peak strength. But with the system, we generally can stay quite constant with the pre-compression load that we apply.
Okay, in our experience, when we try to do in such a mechanism, we found a significant increase in the pre-compression, say about 500% like that. Initially, the pre-compression was 200, say. It rose up to 1 ton even. 200 instead of 200 kg, it even rose up to 1 ton. So in our experience, we felt that it is better to go for gravity loading for pre-compression. So that I wanted to.
Yeah, but we also had some difficulties, and when we introduced the spring, was much better.
Yeah, in fact, we tried multiple options, madam.
Okay.
Even with the spring, we can reduce the effect, but still the fluctuation. Especially when the bricks are soft, that becomes a very, very tedious thing, to control. And secondly, madam, in your in the mean model, your model is not at present not including the contribution of the friction, right?
No, not now. No, it doesn't have it now. Yeah.
But practically, as you one can easily say that the contribution of the friction will be very high when compared to the contribution of cohesion. So
yeah. This is I do understand perfectly. I'm with you on that. But the thing is, I try to go for this method because of this trying to have limited input parameter. Actually, I worked on this method in the past for concrete, and that it was quite okay for what we can do. But for masonry, the friction part is much of relevance, but there are no many studies to try to include this. So the main problem with this model is that we need to work with crack embedded in an isotropic matrix, which is already sitting. We need to include friction, and yeah, we need to try to see how to try to play with the parameter and try to do. But yeah, the other thing is that is quite easy to do. Once you can do analytical formulation to find your stiffness tensor, that is quite easy. Then you can better implement it in time. I mean, it's easier and faster than other complex
sure.
Homogenization scheme.
No.
Of course, there's
Yeah,
some cost that you have to simplify it somewhere, but we are still working on that. And nowadays, I have a new PhD student that started, so I hope he can make good progress on with that.
I mean, can you just advise me in which paper you have published this work, madam? There's on a
Yes,
mean
just if you can find the paper from ZHOU, ZHOU from 2022. So one of my recent paper with this student and Berslaus. Then we publish only the homogenization scheme, so for the brick and mortar, and then in the paper from a EuroC conference from last May, we did this attempt to also include the cracking. But if you drop me an email, I'm happy to share it with you.
Yes,
sure, madam. I will do it, madam. Can you one last question?
Yes,
can you compare your your method with respect to this Eigenstein homogenization, the differences and mechanics? Can you discuss?
Well, that makes use of the mean field homogenization, my method. So we are based on that. It's just that we try to couple with linear fracture mechanics and to try to also include the crack propagation. This is something that is being done for other materials, but not brought forward for masonry. But if you want to discuss more, I'm happy to have a meeting
sure,
or you better.
Nice, madam. Thank you.
You're welcome.
Any other questions?
Yeah, sure.
Yes.
How much repetition of the course testing do you think is needed to have a TRIPLET study result?
Okay, so for shear test, we tried to work with 5 core per inclination, but 3 would be the minimum. And for compression, again, we tried always to do 5 or 6 tests. But yeah, also obviously still 3 is something like lower bound. But if you think about it, you just compare core in compression with the wallet, the core is 4% area than the wallet. So I think that's fine.
And did you do your Brazilian test?
Yes, and then the idea is that this should work when you have a weak bond or a weak mortar, so that you can then get sliding there. Yeah.
Okay, so the fundamental question here is, I'm sure needs much more discussion than what we have here. Why would you go for an homogenization when you can actually almost predetermine the crack propagation in masonry and just use discretization of the model on each side of the crack?
Because if you want to, of course, that are another nice tool, but if you want to have all the input parameters for this kind of models, you need to do too many tests.
No. The question is more generic. Why
Yeah.
do you want to do why are you
Well-
using homogenized and finite element approach instead of using a discrete bracket approach?
Because to have the discrete cracking approach, you need still to enter, I don't know, the softening in shear. Yeah, and then that is, I mean, if you are able to get it out from the cortex, then that is good. But when you cannot touch the building at all,
You can use cracks, you can use cohesion and friction only and just go and just obtain the crack distribution.
yes, but I'm really trying to go when you cannot really do any kind of test at all. So this was my first thing. Actually, the homogenization can also work apart, like try to give the property, let's say, in a smeared way, without implementing in full family for structural analysis. That could be still also one way to go. But of course, if you can implement it, that will be the implemented analysis.
Thank you. I don't know if there are other questions.
No, we don't have online. I was just wondering one question from my side. So far we are discussing the test based on the 4 samples that we take out. How about extending further to including lateral loading? Like, would you consider other mechanisms like diagonal shear cracking?
Yes, but if you get diagonal shear cracking along the interface, somehow that they have to run by the shear response along
Okay,
the
so this can
interface.
actually be used for predicting the other.
Well, then you will need to use model if you really want to do diagonal, but that would be coming from the model itself. So,
So we wouldn't need additional testing.
no, that would be coming from the model, either using the same models when you have to put the interface or the homogenization.
Thank you.
Any other questions from the audience online or from the room? Thank you again very much, Rita,
Thank you
for
very much.
your very interesting presentation. So just to remind everybody and the people online that we have another talk on the 15th of December, also on masonry structures, but from a completely different perspective. This time is looking at non-engineered, very low capacity masonry structures and how they damage and what are the information that we can obtain from field work, and then what are typical strengthening techniques to improve their behavior. This talk will be given by Sebastian Kaminski of our Associates, and we, as usual, look forward to meeting you again online for that particular talk. Thank you very much again for participating, and we'll see you soon. Thank you again, Rita.
Thank you, everyone. Thank you.